Hi. So in this last video, we're going to talk about the notion of good formulations. As I briefly mentioned in the previous videos, in mixed integer programming, the formulation you obtain for your model might have an important impact in terms of performance. So what we're going to do in the next few minutes is discuss why is it so and what we can do in that regard. So basically, in the next lecture, we'll see we'll start seeing solution methods for mixed integer programs. And one thing that is going to become immediately clear is that solving mixed integer programs consists of the task of repeatedly solving linear problem relaxations. So basically, the main mechanism behind solving mixed integer programs is consider the problem as a linear program. And the reason we do so is because we can, as we've seen, very efficiently solve LP relaxations or LP problems using the simplex method. And what we can do is, once that problem is solved, we can infer, information on how to reduce the search space. That process of successively reducing the search space is done until you reach a solution that satisfies integrality. So that means that the notion of performance when it comes to mixed integer programming, solving mixed integer programs, is strongly tied with the sheer number of LP problems you have to solve, of many, the number of these LP relaxations you have to solve. And that's what is going to give a notion of performance. So because once we are talking about the LP relaxation, the formulation itself becomes permanent. It might have an impact depending on the quality of this formulation. It might mean that you have to solve more or less of these LP relaxations, and that therefore there's an impact in performance. Notice that you can't simply rely on simply using notions like rounding, because that's not that. It's too naive to think that solving an mixed integer program, an MIP, is simply solve the linear relaxation, removing the integrality constraints, and then get the solution you obtain around. Is past that. Is way beyond that. So here is a small example to illustrate what is going to be going on. We're going to dive into this into way more detail starting next class, but I want to give you a hint of what is behind, because once you have this notion what is going on, it's easier to understand why is it so that formulations differ for mixed integer programs. So this is a very simple mixed integer problem even. In this case, I have x1 and x2 constrained to be integer, and I have these two constraints. So if I think of how it looks like graphically, so these are the constraints, just like we've seen before. But the main difference now is that instead of having a feasible region that is defined by the whole space of this polyhedral set, actually our feasible region are only the integer points contained within the area defined within this polyhedral region. So, and you can see that this obviously is not convex anymore, because my set is a collection of discrete points. So if I connect these two dots, the point in the middle doesn't belong to the set. And moreover, there is more than one way to represent. There is more than one set of constraints that can actually represent the same collection of points. And you can see in this case here that just to illustrate how bad the idea of rounding can go is, so if I look at the linear relaxation of this problem, the linear relaxation is just basically replacing this with the original like we do, or say greater or equal than 0. And if we solve the linear relaxation for this problem, we have found this optimal solution there, which is fractional. You can see that it's very close to 5, and it's also but it's not the 0.52, but it's very close to 2 and very close to 5, right? So your first instinct could be get this point and perhaps round up to 5. So the coordinate x1, you could round up to 5 or round down to 4. If you round up, you can almost see that the point is not exactly in the feasible region, so it's not a feasible point. So if you round up, you end up with a feasible solution. In the case of x2, x1, sorry, this is rounding x2 to be either 4 or 6. If you round x1, you would end up with either this value, which is infeasible, or this value, which is infeasible, because you would round to this point or to that point. And if you round up and down, you end up either with 5 or 4. It would also be. So the only way to get a feasible point is if you end up rounding x2, sorry, to 4, and x1 to 2. So you get this point. And even if you get this point, it turns out that your optimal integer program point is this one right there. So you are miles away from your optimal solution. So there is no way by rounding this you can get to this point at all. But we can use this information, and we'll see how we use that. We can use this information to say us something on the lines, you know what? Nothing that lives in that direction really matters to solving this problem. So I can then go into a next round in which I only consider this reduced search space, which potentially would take me there, for example, and then I can do similarly like so, which would probably take me here, which could perhaps tell me that I could do something more like so, and so on. So we'll see how that works in the next lectures. But the main point being, we can use that information, but not by simply rounding. So in order to characterize formulations, and with the ultimate goal of being able to compare them, let us first define what is a formulation in a formal setting. So we say that a polyhedral set P is a formulation for my problem, being that problem a set of composed by mixed integer elements. So if P is 0, we get this, and this is the collection of dots that we had in the other picture. A mixed integer set sometimes is hard to see, but suppose x1 is integer and x2 is continuous. So basically your set, instead of a collection of dots, what you will have is a collection of lines like this, because x2 can take any value being real. So this is trying to illustrate x2 being real and x1 being integer. Right. So your feasible set is this collection of bars. x2 can take any value, but x1 can only be discrete. Right. So a formulation, we say that a formulation for x, represented like so, it defined by so P is said to be a formulation for this set if when you intersect P and the domain of the integers for the variables that are integers accordingly, you will obtain the set X. So basically, differently from linear programs where the formulations can be unique if you disregard redundant constraints, in mixed integer programming, you have infinite number of formulations that can return you the same feasibility set, which is quite remarkable, and that's one of the sources of all trouble. So here is a picture illustrating the concept. Let's just pretend for a moment that P is 0. So we only have integer variables, right? So our space or domain is this collection of gray points there. And let's assume that our feasible set X, the collection of constraints within this domain that satisfies, or within this domain that satisfies my conditions of my problem, are these points in blue here. So what you can see here is that there are 3 alternative formulations, which are polyhedral sets composed by a collection of constraints, and they all are formulations for my set X, because the intersection of the polyhedron and the original domain returns me the points that are in the set X. Okay, so you can think of X being the set of little dots, which is what in here. So these are alternative formulations for them. And you might have noticed something interesting about these 3 examples. So the main difference between P1, P2, and P3 is that I can't really tell much about P1 and P2, but P3 is remarkable. P3 is remarkable because it is exactly the convex hull of this original set P, right? So if I do the convex hull of these points, I get exactly P3. And convex hull, when your formulation is a convex hull, there's something quite amazing that happens. If I solve this problem as an LP, so if I solve the LP with formulation P3, and find an optimal solution for any vector C, it could be a vector C that looks like this, or it could be a vector C that looks like that. In any case, you're going to end up finding a solution. Let me get a different color. You're going to end up finding a solution. This case for this. So this is for C prime, like so, and this is C. That is a point that belongs to X. Notice that is not the case with P1 and P2 at all. If you solve P1 or P2 as a linear relaxation, as LP relaxation, you might end up here, you might end up there, you might end up there. These are not points in X at all. But if you happen to have a formulation that is the convex hull of your original set X, then we say that that formulation is ideal, because the number of LPs that we need to solve in order to solve the mixed integer program is the minimum possible, which is 1. You only need to solve 1 LP to find the optimal solution for this mixed integer program. In all the other cases, you're going to have to solve a couple, because you might end up saying this point here, and you're going to have to do something to say, to remove that solution. And we'll see procedures to iterate the process of removing linear relaxation solutions or LP relaxation solutions until we converge to something that looks like a convex hull. So you can think of convex hulls in mixed integer programming as the holy grail that you're searching for whenever you're solving an LP, mixed integer program. So this is kind of, once we have a notion of ideal, we have a way to compare formulations. The formulation that is closest to the ideal formulation is the best, right? Which in this case, we can make it operational by trying to figure out whether one formulation is within each other, if within another. So in this case, I can say that P3 is better than P2 and P1, but I wouldn't be able to say much between P1 and P2. And that's kind of the concept we're going to explore in the next couple of slides. So first of all, with this notion that ideal formulations are those that are the convex hull, I'm putting this proposition here just to, this is a corollary of the resolution theorem we saw in lecture 6. And we saw this a couple times now, that the convex hull of a set X is a polyhedral set, and all its extreme points will belong to this set X. So this proposition is basically showing what we had in that picture with that green polyhedral. So if the polyhedral is the convex hull, it means that the extreme points belong to X. And these are going to be the candidates to optimal whenever you're optimizing something that is linear. So that tells us the following, that if you somehow have available the convex hull of your set X, you can replace X by its convex hull and solve this problem instead to obtain a solution for this problem, right? So this X has a formulation AX less or equal than B, it's in a mixed integer set, and the convex hull is such that you get the same formulation and your X's are relaxed. And because it is that being actually the convex hull, then these can be replaced. That's the ideal world, but in practice, this is typically not possible. So methods to find convex hulls are quite, so basically convex hulls, they typically have a really large number of inequalities, and characterizing it's truly a big challenge. There are people in the realm of combinatorial optimization and look at it at combinatorics in general, and they develop methods in which you can approximate convex hulls, and there is a strong connection between those and the efficiency of mixed integer program solvers. So there is a really interesting research area that is very active, by the way. But in general, this is absolutely not possible for practical problems. But nevertheless, because we know this notion of ideal formulation, we can then define a structured way, a pragmatic way to compare formulations. And that is done by what we can see here. So basically what we do is the following. So we have a set that it's a mixed integer set, and we have two formulations P1 and P2. We will say that P1 is a better formulation than P2 if we can show that P1 is contained within P2, because that will have as an effect typically leading to a smaller number of LP relaxations that need to be solved in order to solve the original mixed integer program, and we say that that's better because that is a better performance. Okay. So in this case, just in these two pictures, you can see that P1 is not exactly the convex hull. It's pretty good. And if I were to compare P1 and P2, in this specific case, P1 is a better formulation than P2 because it can be shown to be within P2. Basically, you can think of the amount of fat that you have to remove to get this lean cut that is a convex hull. You know, you have less fat to remove here than you would have with P2. And you will see that the methods we have to solve mixed integer programs, they're nothing more than looking at these formulations and little by little, just like, you know, when you're cleaning a specific cut, or when you trying to remove this nasty outer shell of dirt and not good, and you want to get to the good stuff, which is right in the center. So it's this process of peeling and removing layers, which is, easier, will require less cuts or less iterations than this in general, of course. This is what we're gonna guide us. This is what gonna guide us in the process of telling whether a formulation is better than another or vice versa. It might be so that we are in a situation where these problems, they actually it could be so that P1 and P2, they have different domains. So it might be so that you have a formulation with different numbers of variables and constraints, which makes this analysis a bit more complicated. So basically in this case, what you have to do is to try to bring the two sets to a common set of dimensions. And you do that by means of projection. So say P1 had an extra variable that is not present in P2. So you have to project P1 on the variables that are available in P2 so you can compare them. We will do an exercise in which that is the case, and we'll rely on projection to show that one formulation is better than the other. But it's still, when they don't have the same number of formulations, it's still possible, but you do have to make sure you can bring them into the same space, say x1, x2, so you can show whether there is a relationship in which one is within another. Yeah, so that's it. We'll stop here for this lecture, and I'm looking forward to see you in the next lecture. Bye-bye.